Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to just do a quick review of the background information on designing cooling towers. So this is a very brief summary of what we did in class. Our basic terminology that we're needing and some basic facts. We're going to be relating this back to humidification and psychrometric charts. A cooling tower's goal is generally to cool water by mixing it with air. Okay, so the water falls through rising air. This is going to be like a stripper. It's gas phase controlling, and we want to maximize the turbulence to get the best possible mass transfer, and this is frequently done instead of just by raising flow rates, but we'll do it with packing grates, troughs, something like that. The minimum temperature would be equilibrium, but that would require an infinitely large tower, so in practice we're not going to get any closer than 3 degrees C above the wet bulb temperature. And we're also going to have to worry about water loss due to evaporation. Now, two other terms that we sometimes use are listed over here. So the approach of the cooling tower is the difference between the temperature of the liquid that's leaving the tower and the gas or the air that's coming into the tower. That's the approach temperature. And the cooling range is the difference between the inlet and outlet temperature for the liquid water. There are a bunch of variables that we're using. We are using L for the water flow rate or water flux. It's kilograms per second per meter squared, and G for the dry air or bone dry air, BDA, kilograms per meter square per second. The temperatures will be in either degrees C or Kelvin. Humidity of the air in kilograms of water per kilogram of dry air, and the enthalpy in joules per kilogram of dry air is listed here. And if you need it in kilojoules per kilogram dry air, the yellow marks, okay, are the unit conversion for that. This is based on temperature in degrees C, not Kelvin. And as we discussed, instead of a y-x diagram, since x is always equal to 1, we're instead going to use enthalpy of the gas versus temperature of the liquid for our operating diagram. Our equilibrium curve will be the equilibrium for the gas fully saturated with water, and then we will draw in our operating line. And because it is really essentially a stripper, then it will be below the equilibrium curve. If you do energy balances on the total tower, or on just the bottom half of the tower, or just one little differential slice of the tower, we see that an energy balance is the gas times its enthalpy change is equal to the liquid times its enthalpy change, whether we're doing it differentially or over a large slice. And if we look at now how that heat transfer happens, within this little slice, it's going to be due to primarily convection, so we'll use a heat transfer coefficient H. And so I have the amount of heat transfer by the liquid is equal to what happens for the gas, but it's also equal to the heat transfer by convection within this area or volume. And we can calculate how much heat is lost due to vaporization by figuring out the flux, the movement of the water from one phase to the other, molecular weight of the water, the surface area, and the heat of vaporization. Now notice this brings chapter 6 back into the game, and so we have our Fick's law expression here. And we can use this then to estimate y related to the humidity. And we can combine these various equations so that I end up with a relationship between the change in HY, the enthalpy of the gas, to the change in the liquid temperature is going to be related to the heat transfer coefficient over the mass transfer coefficient, with molecular weight of air and total pressure well, to get the units right, basically. And so this is going to give us that relationship that when we were doing absorption and stripping was the negative kxa over negative kya. This is our relationship. So energy and mass is our energy, or is our balance that we get. So if we wanted to use this to design a cooling tower, the steps are essentially the same, but the diagram is different and our driving force is different. So start with the plot of our equilibrium data. And in our textbook, the data is on page 650 to allow you to plot it, or we have an equation here. And then you're going to plot the operating line. So we assume that you know what is coming in, the air quality is like coming in, and we know what the liquid we need to have, both at the inlet and the exit. And so your first point is going to be the combination of the gas inlet and the liquid outlet. Our other point is going to be the liquid inlet, but we don't know what the enthalpy of the gas coming out is. And so typically we get that by figuring out our flow rates, and the slope of the operating line is LC sub P over G. So I can take my starting point and the slope to extend that all the way to TL2 and use that to figure out what HY2 needs to be. Now, if I'm wanting to figure out the amount of packed area, or the volume of where I'm having mass transfer happen, what I'm going to do is I'm going to plot my lines to figure out what is happening at the interface. And those lines in this case are going to be negative the heat transfer coefficient over the mass transfer coefficient with appropriate units, so kg, p, and molecular weight of the air. And do that for a variety of points, and then we're going to do this so that we can get to numerical integration. If you look at this, these are going to intersect the equilibrium curve at the point M over here. And this is going to be HY at the interface. This is HY on the operating line. And that distance vertically between these is going to be our driving force. Okay. We're going to need to integrate that with changes in H sub Y. So break this line up into even partitions and draw these lines, and then you can integrate numerically. This portion is the number of transfer units. This is the height of a transfer unit, G over MB, and then our KGAP. Multiply those together, you get the total height of packing. If you're not using film coefficients, we can also use the overall mass transfer coefficient. And this one is easier because I don't have to figure out what those interface points are. All I'm going to do is look at the difference between HY and HY on the equilibrium curve for various values of T sub L. So generally I draw vertical lines through my graph at even spaced intervals and measure that difference, HY star minus HY. That's the denominator in my integral. And then evaluate this for different chunks of DHY. So it's not the area going this direction, it's 1 over this height difference, but my slices are going this other direction. Okay? Which when you see the example, you're going to see that that changes. I had to modify my numerical integration program that I've written. Okay, but this is the basic calculation technique. We're going to look at an example in a few moments. I want to talk about one other important design feature, and that is that we need to figure out what the airflow rate is. Normally, the water cooling flow rate is determined by the process. So then I just figure out how much air is required to make that happen. And so we're going to do the same techniques we did with absorption or stripping. We're going to figure out where our pinch point is. So we have a known point, we have a known exit temperature. Draw so that you get that pinch point, and that's going to get you the G minimum. Now our slope of this minimum or extreme operating condition is L times C sub P for the liquid divided by the gas flow rate that's the extreme. In this case, it's a minimum. We're going to calculate, figure out what the slope is, and then calculate what G minimum is, and then multiply by typically 1.3 to 1.5, and use that then to calculate G. Once you've done that, then you're ready to go back and do the process of figuring out the height. So this concludes this video lesson. We're going to next look at a couple of examples, and then we'll have one more little chance to look at other ways that we can do cooling towers, other things we can do. Thank you very much for your time.